coming all the way to talk to us about your work. And I think some more may gather with time, but I think it's time to make a start. So I thank you one and all to kind of be here to this gathering. We'll make a start. Dr. Arpan will say a few words perhaps about Dr. Ghosh, and then we'll make a start, and post that maybe we can take some questions and interact with each other before breaking out for lunch. Thank you all. Dr. Arpan, just a few words about your friend.
Now, if I'm being considered as Sujay's friend is very good. The reason that we picked up Sujay is that I'm sure the way he is working, after a few years, it will be very difficult to get Sujay here. So that's the reason we thought that we should do. So just for your information, this is a new initiative from our Karnataka Endocrine Society that we are trying around 3 to 4 times a single speaker in our country whom we think is doing some original work, and just pure endocrinologist here. There's nobody else will be there to interact, so that on good topic. So I think all of us know that Sujay is a professor of endocrinology in IPGAMR Calcutta for quite a number of years now, and he has a lot of work, particularly in this field of molecular endocrinology. So we'll hear to this topic about liquid biopsy nodule. Sujay, please.
Given me this wonderful opportunity to speak before you. More importantly, I got to sleep for 8.5 hours last night. I think that itself was a privilege for me, because you don't get time when you're working in the hospital or where you're trying to travel, come to a city, deliver a talk and run away. The bad bit is that most of you would have heard this talk during ESICON a couple of months ago, and I actually wanted to talk on something else, but Orpanda insisted that this is something which is important and people would perhaps like to listen more than once. So some of my older DM trainees and friends are here. They would have known that maybe 5 years or 6 years ago in the Department of Endocrinology, IPGMER, we had nothing. We had to start from scratch. I did not even have a chair to sit on, forget about a pipette. So we've managed to actually put things together, and I now have a wonderful, wonderful team of juniors. I have 8 PhD students who are my backbone for research. I right now have 27 funded research projects, which I think is dramatic for a period of 5 years. And I get to present the work that the team is doing. So, it's not that I am the one who's done all of this. You can say, okay, a lot of the enthusiasm and the concepts were mine, but it's the team which has done the work. So the good thing is that this is an endocrine audience, so I don't have to talk about the background about thyroid nodules and stuff like that. A very quick recap, that we know that this is the commonest endocrine tumor or malignancy when we talk about thyroid cancers. And importantly, that in the last 15 to 20 years, people have found out possible molecular mechanisms of thyroid carcinogenesis. And about 75% of all thyroid cancers have some known driver mutations. Now, these are mutations which are not necessarily inherited. These are mutations which can happen over a period of time. So if you're looking at germline, you will not get these mutations. But if you're looking at the tissue in particular, you will get this mutation in about 3/4 of the individuals. And again, when you talk about thyroid cancers, 95 to 96% of that will be differentiated thyroid cancers. And amongst that, you will predominantly get Papsia thyroid, followed by follicular thyroid cancer. For the sake of research, you can't take every kind of thyroid cancer, so we only took differentiated thyroid cancers. We excluded all patients who had medullary thyroid carcinoma for the purpose of study. But I can tell you now, we now have about 15 patients in whom we have defined what we found in medullary carcinoma thyroid as well. We'll talk about that some other day. So as endocrinologists, what we usually tend to do is, once somebody comes with a nodule, we clinically palpate, take a good history, do a thyroid function test. If the TSH is suppressed, the algorithm changes a bit. Otherwise, you then ask for an ultrasound if it's palpable. Now, all of us are using various kinds of scoring systems. You might be wanting one, the radiologist might be giving something else altogether though, but hoping that your radiologist and yourself are on the same zone. And you are told, I think most of you will agree that you are using ACR thyroids, right? Now, remember, the ACR thyroids is not the be-all and end-all of thyroid ultrasound. Because one of the major things that the ACR titers does not tell you is the lymph nodes. You should ask for the lymph nodes separately because they might give you additional information. And I think the ACR titer is a bit biased when it talks about a solid nodule versus a heterogeneous nodule, a mixed nodule. Anyway, whatever you do, we all know that, certain points on that ultrasound tell you that this is possibly more likely to be malignant or less likely to be malignant. And most importantly, I think the ultrasound tells you should you be doing an FNA or not. That's, to me, the most important information that comes out of the ultrasound. So I was telling you, it does not tell you anything about the lymph nodes. And this is one of our publications which again tells you that the thyroid tells you only about the possibility of malignancy. Now, if you have a patient in front of you and you say there's a 26% chance of malignancy, what does it mean to him? It means nothing to him. Because in the sense, when you're making at an individual level decision, you either operate or you don't operate. So that percentage risk probably does not make much of a difference. And we are all using the Bethesda system of classification of looking at thyroid FNAs, which again, you probably know that about a year and a half ago, there's been another further modification of the Bethesda reporting system. But to cut a long story short, we all are worried in 3 and 4, what we call the indeterminate thyroid nodules. And that is where you and I are struggling to decide. You're not much worried about 5 and 6, you send them to surgeries. The 2, we follow up, but remember 2 also has a 4% risk of malignancy. Even though we are saying Bethesda 2 is benign, it has a 4% chance of malignancy. So that's the reason why we follow them up and repeat imaging as and when required. Now the indeterminate group is where we all have a problem. I don't know about surgeons here in Bangalore, but in West Bengal what happens is, if you send them to the surgeon, whatever you tell them, they will, even if you don't tell them to operate, they will operate. And it's usually a hemithyroidectomy. And if you do a hemithyroidectomy in patients in that indeterminate thyroid nodule group, 75% of them will come back as benign. Now you tell them, we had a good look and you did not need the surgery. So that surgery was not needed. So you've subjected them to surgery that was not needed. The rest of the 25%, the report will come back as malignancy. You then tell them that we found that this is cancerous, we have to go back and we've got to reoperate and remove the rest of the thyroid. So in either of those 2 cases, we are not doing the right thing. Either we are operating where we shouldn't have, or where we are subjecting an individual to 2 surgeries where 1 would have sufficed had you known that this was malignancy to start with. Now, this indeterminate group is not too small. It's about 20 to 30% of all your FNAs, depending on how good your cytopathologist is. So if you're looking at 20% or 30% of your patients, you're not doing the right thing, then you need to do something about them. And again, that hemithyroidectomy versus thyroidectomy. And therefore, what I've already told you, this is the risk of malignancy. What the Western world has started doing is, where available, they're using the FNA samples for doing certain molecular genetic tests. Now again here, even in the Western world, there are 2 schools of thought. One would preserve the FNA material so that they can subject it to genetic tests later on if required, or they would send the patient for a second FNA. So again, there's a problem there. Even if you have a second FNA or a first FNA, you are subjecting that individual to an individual skills level of, where is the ultrasound, where is the needle, and where is it going in. Now imagine the problem gets even worse. You have a multinodular goiter. You have 15 nodules in the thyroid. Are you going to FNA each of them, or are you going to do genetic tests in each of them? So that's a problem. But still, molecular tests where available is useful. And it has evolved over a period of time. Just like our TSH assays, you now have the 3rd generation of molecular tests which are relatively validated. And if you look at these tests, they're essentially based on 2 things. Either you're detecting a driver mutation and saying this is this, or you're looking at RNA. Either you're looking at microRNA or you're looking at mRNA to say whether this is benign or malignant. So I've just tried to highlight that, where you're trying to say this is benign or malignant. Now the challenge and the problem is the tests are not sacrosanct. It's either a rule-in test or it's a rule-out test. And what you essentially want is a very high positive predictive value and a very strong negative predictive value for the test to be of use at an individual patient level. For example, you find a driver mutation of RAS. That can be there in a follicular adenoma, that can be there in a follicular carcinoma. So that driver mutation does not help you. On the other hand, if you have a BRAF V600E positive, that helps you to say, okay, this is Pap-C thyroid. Or if you have a TART positive, you know this is Pap-C thyroid. So this also has certain limitations. So number one, you have to have an FNA to do these molecular tests that are commercially available in the Western world. In Indian currency, a single test costs about 1,50,000 rupees, which I don't think many can afford. Of course, there will be several who can afford. And it has unacceptable negative predictive value. So even after that, what people are trying to do is they are using AI. So this is what I found on an FNA molecular test. This is what my Bethesda is. This is what my USG findings are. Let me put everything together and come up with. So it's a better informed decision making. That will happen if you use tests like this. Of course, we don't have that available in India on a commercial basis. I do understand some of the corporate houses are actually trying to come up with a panel of tests. CMC Vellore actually before Dr. Thomas Paul moved out, I think they were doing it, particularly in the endocrine surgery department, they were actually looking at things. But I still don't know where things stand there. Now the more important issue is, now you've operated, you know what kind of surgeons we have, right? When you look at TSH values post-surgery, some of them you still find the TSH is near normal, telling you clearly that some amount of thyroid is left behind, right? Now, do you know whether the tumor was appropriately removed or do you have residual tumor? You don't know, because even in the best of hands, such things can happen. So, where do you stick in a needle to find out on FNA if the cancer is still there? You can't do it. What about those patients whom you are following up for thyroid cancers? What are we doing right now? We are looking at the TG values and the anti-TG values. Whether stimulated or unstimulated or RH stimulated, TSH stimulated is questionable, right? And you know there are fallacies of that. There are problems with that. And more importantly, a differentiated thyroid cancer might come back as an undifferentiated thyroid cancer. Then your TG is also out of the window. So you cannot use those tests for recurrence detection of thyroid cancer. So I've tried to set the stage that this is where the knowledge gap is. Now a little bit about liquid biopsy. Now it's a very fancy, fashionable term, essentially telling you when you're talking about a tissue biopsy, you stick in a needle in the tumor, in the tissue, and you take a sample and you say what's what in terms of the histopathology as well as the molecular biology. But when you take samples from a place which is not the primary area of the tissue, neither a MET, and you use that body fluid to analyze, to either detect, prognosticate, detect recurrence, or make any diagnosis which is not from there, from another body fluid, that is essentially liquid biopsy. So the liquid biopsy should be able to tell you whether the cancer is there or not. Number two, the tissue of origin. You take a blood sample and you find something and then you say, there's a cancer, but where is the cancer? You need to be able to pinpoint the tissue of origin. Now you should be able to say what the staging of the cancer is. What genetic mutation is there in the cancer? I'll just give you an example. Currently, if you are getting an FNA from a nodule which says that this is Pap-C thyroid, you're happy, right? But you know there are variants of Pap-C thyroid. So you can have a BRAF positive Pap-C thyroid. You can have a TERT positive Pap-C thyroid. You operate a BRAF positive Pap-C thyroid, you're almost certain that nothing's going to happen in that individual's life in the next 20 years. It's not going to be that aggressive. A TERT positive Pap-C thyroid is going to be far more aggressive. So it also gives you that perspective that, you know, what am I dealing with? If there are lymph nodes in a TERT positive Pap-C thyroid, you better tell the surgeon to remove all of them. So you will be more aggressive. So just an FNA diagnosis, the outlook could change if you have a molecular diagnosis. And all of you would probably be now knowing that in several of the cancers, including lung cancer, there's something called an EGFR mutation. So people are diagnosing an EGFR mutation in the lung cancer and deciding what chemotherapy to give. Once they've given a chemotherapy, they are looking at blood tests of the EGFR mutation to say, is the drug responding? Is the cancer coming back? Do I need to add another second regime, or do I need to up titrate? So you will be able to know what treatment works, is it working or is it not working, and what treatment might work, and if there is any residual tumor or whether there is any recurrence. So that's the EGFR mutation kit, which is now commercially available even on the Roche machine that you are using in your hospital. So this is a picture that I've taken from New England Journal of Medicine, which tries to tell us about the possible sources of liquid biopsy. So I was actually trying one of them in our patients of craniopharyngioma, because even in craniopharyngioma you have the BRAF gene which is positive. So I already had the primer ready in my lab. I was trying to take out CSF to see whether it's working or being able to detect recurrences. I wasn't successful. But even the CSF might be able to tell you it can be a source for some tumors. The saliva, pleural fluid, and what we are going to talk about is peripheral blood. Now, if you're looking at peripheral blood, you can look at so many things in peripheral blood. Depending on the biology of the tumor, you might have circulating tumor cells, you might have exosomes, and you can have cell-free DNA. So we are going to look at only cell-free DNA in our study. Now, when you're looking at cell-free DNA, it can be a circulating cell-free DNA, or it can be a cell-free DNA which is bound to a lot of vesicles. Now, a little bit about cell-free DNA. What is this concept of cell-free DNA? Well, in normal health, some of our cells are dying every day. Once a cell dies, due to whatever process, whether it's necrosis or apoptosis, the cell breaks down. Once the cell breaks down, from the nucleus itself, the DNA also breaks down and comes out in circulation, and is removed from circulation as well after a while. But depending on your cell turnover and amount of cell death, you will have certain amount of cell-free DNA circulating in your body. So if you have got severe inflammation, severe trauma, burns, your cell-free DNA is going to increase. Similarly, if you have a tumor, that tumor is going to have a higher cell turnaround, and you will have increased amount of cell-free DNA in the blood. That's the concept. So if you take a blood sample and find that your cell-free DNA is more than someone else or the general population, then you have a problem of either infection, inflammation, or cancer. Now, for our study, we first excluded people who had an active infection, active trauma, inflammatory disease, to find out normative data for individuals where you have no other problem, and compare it in the benign individuals with benign thyroid tumors, and then figure out what happens in those with malignancies. Now, this concept of cell-free DNA is already now documented in medical literature in colonic carcinoma, in ovarian carcinoma, and breast cancer. They've seen that the cell-free DNA goes up to some extent. Depending on the tumor load, the cancer subtype, it will go up. So if you're looking at the cell-free DNA, what do you look at in the DNA itself? One, you can look at the concentration of the cell-free DNA, right? Then you can look at these driver mutations that I told you cause thyroid cancer. So if you're saying that the cell-free DNA has gone up because of the thyroid tumor itself, then that bit of the DNA which is circulating should have those driver mutations to tell us that it has indeed come from the thyroid tissue of concern. The copy number, there might be alteration, there might be gene fusions, and there might be other epigenetic changes. For example, DNA methylation. So all those changes can happen in the DNA itself. So I've already told you about what the possible applications of cell-free DNA is. So this is conceptually is true for any cancer, not just thyroid cancers. So coming to our first publication, which we published in the JCM a couple of years ago, where we tried to determine the concentration of cell-free DNA in this indeterminate category of people to try and see whether we could predict whether an indeterminate nodule was benign or whether it was malignant. So I'll skip the sample size calculation. The only reason I wanted to show this slide is not because I want to confuse you about molecular biology or anything like that, is because you see what we are using. We are using a standard DNA isolation kit, which essentially costs 40 rupees per patient, 40. A spectrophotometer is there in every lab. Every hospital has a spectrophotometer. The qubit we use for the research purpose to validate the concentration of the cell-free DNA. But the spectrophotometer every lab has. So you use a commercially available DNA kit and check for the concentration of cell-free DNA in the biospectrophotometer. It will tell you the concentration of cell-free DNA. So this bit will not cost your hospital or your lab more than 40 bucks. So who did we take? So we've taken a significant number of people, about 223, where we did what you and I do in everyday clinical practice, that is history taking, a blood sample for thyroid function test, an ultrasound and an FNA. What we did additionally was, when you took the blood sample for the thyroid function test, even before the FNA was done, you took sample from that and you separated the DNA and you also measured the cell-free DNA concentration and you did not tell it to anybody else involved in the study. And people, this is the histopathology finding of everyone who underwent surgery. So, if you look at, we purposefully excluded those who were Graves' disease patient. We now actually have another cohort of Graves and we've defined normal Graves cell-free DNA concentration because we found 3 patients with Graves with malignancy now on the basis of our study. That's altogether different. We excluded multinodular goiters and we excluded Bethesda 1 because there we didn't know what to do. So we divided our group into what we presumed would be benign on the basis of Bethesda 2, the 5 and 6 whom we presumed to be malignant, and the 3 and 4 is our indeterminate group. Now whatever we presumed, we subjected them to surgery and we had a histopathological diagnosis that whether they were benign or malignant, because that's your gold standard. So if you now split the results in 2 groups, it's color coded, and let's first look at the left side. You have those who are benign and those who are malignant in Bethesda 2 versus 5 and 6. And we looked at their baseline cell-free DNA. So you can see in the benign group, the cell-free DNA was around 22, and in the malignant group, the cell-free DNA was about 96. So we did an ROC curve. Probably you won't be able to appreciate that this is at all an ROC curve, because if you see here, that's the chink. It is so good, too good to be true. And what is more important is, we came up with a cutoff of around 69, but you might argue and say, so if it was 65, so it was benign, and if it was 70, it was malignant. There was no noise. Everybody who was benign was below 25. Everybody who was malignant was above 75. So it's very clean. There's nothing in between, which is very good for a test. Otherwise you might have a great ROC curve, and yet you might have problems when you are seeing patients. Now, we then looked at the ones who had indeterminate thyroid nodules and had undergone surgery and has a diagnosis. We did not know who has what diagnosis. We applied that cutoff in that indeterminate nodule group, and we found the sensitivity was 90%, specificity was over 90% as well. Now, this result actually we are going to modify, in the sense we now have a bigger cohort and we'll have a better cutoff. That's we've thought of number 1. And number 2, one of the reasons that some of the ones that we classified there as benign, we've learned from mistake, because Chitra is here, she will know our histopathology department, because this was one of the earlier patients that we had sent to our department. We don't send it to them anymore, because someone with a big tumor, you need to look at various sections. You just can't say this is benign and this is malignant. Why I am saying this is because we are in the process of publishing our NIFTP data. I now believe the molecular tests more than my histopathologist. It is so strong. The data is so strong. So anyway, but this, and if you look at Cohen's kappa, it's 0.92. So what do you mean by a Cohen's kappa, for example? Let us imagine you have 3 radiologists. Each one of them is looking at a mammography plate and saying whether it's benign or malignant. And then you have someone else who's actually gone and operated, and you have a biopsy proven gold standard data. So out of 100 plates, maybe say 10 were malignant and 90 were benign. The first radiologist said that 93 of them are benign. So he's misdiagnosed or mislabeled some of them, which were actually malignant as benign, or vice versa. So when you are talking about a Cohen's test, it tells you your concordance with your gold test. So anything above 0.9 is thought to be almost as good as your biopsy. Now, the fact that these patients with cancers in our cohort had raised cell-free DNA, who has told you that the cell-free DNA rise is from the tumor per se? So we went back to these patients post-surgery and rechecked everybody's cell-free DNA. And we showed that the ones with cancers where the cell-free DNA was raised, post-surgery it had all normalized. Just to let you know, we have again another cohort of residual tumors that we've diagnosed, 11 cases now, where we've diagnosed residual cancers, where the cell-free DNA had not normalized post-surgery. That's another study which the Endocrine Society of India has actually funded us. So again, we know therefore that this source of cell-free DNA is the cancer itself. The next slide is entirely exploratory because the study was not powered to look at this. What we did was, okay, you've got cancer and we found that your cell-free DNA is increased. But what about its relationship? That raised value is okay, it's above 70. What happens if it's above 90? What happens if it's above 110? It correlates pretty strongly with the stage of the tumor, which again sounds sensible because it will depend on the tumor load. So the higher the tumor load, more is going to be the cell breakdown, more is going to be the cell-free DNA concentration. That we have shown as exploratory data in this study. We are now following this up prospectively in a powered study to try and show whether this is really the case. So you can stage. So somebody has come up and he's in, and you've got the cell-free DNA of 120, you will probably have to investigate the patient for spread of the tumor already. So if I summarize the findings of this bit of the study, I've shown you that cell-free DNA is high in malignant versus benign ones. I've shown you a cutoff, that there is very good concordance between our test and the histopathological diagnosis, and that there is graded increase in cell-free DNA depending on the stage and invasion of the tumor. Now I've already told you that the cell-free DNA is raised in our patients of thyroid nodules with cancer. And I've told you it normalizes post-surgery. Now, can I diagnose what histopathological subvariant of cancer that was? So we then now looked at, because we had stored the cell-free DNA of all of these patients, we now tried to look at the driver mutations of known driver mutations of thyroid cancer within that cell-free DNA. And we chose a panel of 8 genes, because when I showed you third generation FNA genetic testing, you would have seen there was 113 known driver mutations in thyroid cancer, which accounts for 75% of driver mutations in thyroid cancers. But 75 to 80% is these 8 genes only. And because obviously I did not have money to start NGS for everybody, for all of those genes in 300 patients, we thought as a concept, why don't we start with an 8 gene panel, which will tell us what happens in most of the cases. So if you look at patients with malignancy, about 75% of them we were able to find a mutation. That's what you are expecting. And in about a quarter of them, you did not find any mutations. Why? Because they were either outside of those 8 gene panel, or they were people with no known gene mutations. And all of them, without those known mutations, turned out to be papiziothyroid. The rest, depending on what mutation you had, we could predict what subtype of thyroid cancer they had. Now the problem comes when it comes to RAS mutation, because you know RAS can be positive both in PAP CA thyroid, in follicular CA thyroid, as well as follicular adenoma. So the presence of RAS does not tell you whether this is benign or whether this is malignant. In the ones where it's benign, where the mutation was positive, they were all RAS positive benign tumors. Now if you combine the cell-free DNA concentration data with the RAS mutation, you will straight away know what's happening. Cell-free DNA is high, RAS is positive, this is follicular carcinoma. Cell-free DNA is normal, RAS is positive, this is follicular adenoma. And the rest that were negative was a mixed bag of everything under the sun. So this is what we did. We combined the cell-free DNA concentration data with the mutation analysis. Cell-free DNA is high, mutation is positive, you know for sure what it is. If it's high with a mutation negative, it's classical PTC. If the cell-free DNA is low, mutation positive for RAS, it's follicular adenoma. If it's negative, it's everything else. So we then tried to look at the performance of the mutation alone, because you now realize that you actually need data of both the concentration as well as the mutation positivity. But for the sake of the reviewers, we actually had to show them what happens if you're looking at the mutation only. So all of the mutations that I'm talking about, we validated by doing Sanger's and next-gen sequencing. So that's in the plasma, that's in the FNA material, and that's in the tissue. Because whatever mutations you found in the blood, you've got to go and show that that's there in the tissue, whether it's the FNA samples or whether it's the histopathology samples. That we have actually done. And we've published that in the European Journal of Endocrinology. So what are the limitations now? So the first one being that 25% of the cases don't harbor any of these known mutations. And RAS can be there both in follicular as well as benign lesions. Now whenever we talk about genetics, we go back to our undergraduate days where we were taught about the central dogma of genetics. And what is that? That you have one gene, that gene codes for one protein. And as if everything in genetics is that simple. Gene, messenger RNA, protein. Now we know that only 2% of the genes are protein coding genes. And the rest of the 98%, at one point of thought, it was thought that that was junk DNA. And if you look at the cell per se and circulation, you will find so much of RNA there. Small long non-coding, small RNAs, circular RNA, long non-coding RNA, micro RNA. There is so much there, and we all thought this was junk. God is not such a big fool. There must be some role of all of these things in what is actually happening. So we've got to look at these bits now. For example, you might have a gene, but it's not translating into something. That can be because of certain epigenetic changes. You might have histone modification, DNA methylation. It's like a book. If you read a book on the same page multiple times, it will open that page. So that might happen with histone modification and methylation. Similarly, the function of whatever you are doing is dependent on these transcriptomes. That is the long non-coding RNA, the microRNA, the messenger RNA, the mRNAs. All of that might actually be modifying the expression or whatever happens at the level of the cell in terms of its proliferation, its destruction, and its growth. So we then tried to look at, number one, the long non-coding RNAs. Because, the microRNAs, Nikiforov and his team has come up with that particular kit that you saw. So we then thought, let us look at long non-coding RNAs. Now, there are several ways when you can actually do research like this. Number one, you can go cherry picking. Somebody's looked at certain long non-coding in this cancer and somebody's looked at that. Why don't I go and jump in and look at that? The more scientific way is two. Number one, you either go for a database-based screening. Now, everybody who's done studies everywhere, whether it's a cell, whether it's an animal, whether it's a human tissue, that data gets put into, of long non-coding RNA goes into this database. So you figure out which of these long non-coding RNAs have been previously reported in all of these models, in whatever studies that has been done, that is either upregulated or downregulated in cancers. So that is how we actually chose certain long non-coding RNAs. We validated this with another thing. What we've done is, we've taken 20 patients of cancer and 20 patients who are benign. And we've done a pooled transcriptomics. And we've seen that there's one or two more here and there that is actually either upregulated or downregulated. So anybody wanting to do studies on microRNA, long non-coding RNA, this is the basic method of choosing what you do. Unfortunately, whenever a paper comes to us, we see somebody has looked at X or Y or Z, God knows why. So you have to be scientific in the way you choose certain, transcriptomes. So these are the long non-coding RNAs which we've looked at. So what we've done is, we've still had the blood sample before surgery, and you have the FNA and you have the histopathology samples. So we've looked at the expression of these long non-coding RNAs, similar to our first publication, in a discovery cohort, then validated in a validation cohort. So as you can see, the PVT1 expression is grossly changed. So I'll skip some of these slides because I think I've been boring you guys for way too long. So if I summarize the plasma sample data, you can see MALAT1, PVT1 and BANSER are the ones which are different between the benign versus the malignant ones. So once we've looked at that, we then tried to find out, we did an ROC to find a cutoff for these values, for these three long non-coding RNAs, and look at their performance in our ability to differentiate benign from malignant. And it did pretty well, more than 95% sensitivity and specificity and good positive predictive value for PVT1. PVT1 particularly did very well. MALAT1 did not do that well, even though statistically significant, and similar was BANSER. Now when we found these long non-coding RNA expressions different in plasma, we then wanted to cross-validate to see whether the same changes were happening in FNA as well as the histopathology tissue. We went and did that as well. So of the three long non-coding RNAs that we had narrowed down, we realized that PVT1 could be a potential marker for thyroid cancers. Now you know that the long non-coding RNAs will essentially interact with microRNAs to do whatever they are doing. So we then went back to database to figure out which of the microRNAs interact with PVT1 in the thyroid tissue. And we identified the three known microRNAs which interact with PVT1, which act at the level of the thyroid tissue. So we then went and looked at these microRNAs in the plasma, in the FNA, as well as in the histopathology. We looked at their expression. And as you can see, the one in the middle, the MIR 1493P, which is actually it accounts for majority of that kit that the microRNA kit has. It contributes to the best discrimination between. We didn't know at that point of time. We later found that out. So if you're looking at this microRNA, it is down-regulated in plasma and tissue samples. So we then thought, okay, let's try and figure out the mechanisms, because in the future, if you are thinking of that you're going to change treatment, you would want antisense oligonucleotide or whatever, you need to know the pathway through which this carcinogenesis is happening. So the common target of PVT1 and this particular microRNA, we wanted to know which protein does it alter so that we can knock out that protein for cancer therapy. So there's again another database in today's world where you can actually put these two data together and do an analysis. That's called the cake pathway enrichment analysis, and we found out that there's a protein called MYC which actually changes in patients with thyroid cancer. Now that's one thing to know, that this long non-coding RNA will be upregulated, this microRNA will be downregulated, and then this protein expression will increase and cause carcinogenesis. So that's the hypothesis now. Now to do that, to prove that, you actually have to, in a cell culture model, do a knockout study to actually show that this happens. So we went then and did a knockdown of the PVT1 to see what happens to the expression of the MYC protein. The moment you knock down the PVT1, you see that the MYC protein expression has gone down. We did a Western blot to actually show that the protein expression of that has gone down. And now that you silenced PVT1 in a cell culture model, we got a cell line which is a papillary thyroid carcinoma cell line. We bought that cell line. By knocking that PVT1, we showed that the proliferation of that cell line got diminished. And there was more. As you can see, there is apoptosis of the cells when you knock down that particular model. Now, when you knock down the PVT1, what happens to the microRNA that I was talking about? You can see the expression of that has gone up. And this is the relationship now that you can see between PVT1, MYC, and that particular microRNA. So if I summarize that data, the PVT1 goes up, this microRNA goes down, and the MYC protein expression goes up. So if I summarize this bit of the data, number one, we were able to identify the driver mutations that I talked about in the plasma itself. We showed that the cell-free DNA concentration in the malignant patients were increased. With that, if the mutation was there, you had no hesitation to say that this is a cancer and this is this subtype of cancer. And we've also shown how PVT1 MYC interaction happens. Now, what's the translational significance of the work that we've done until now? So if I kind of summarize in one slide, if the cell-free DNA is high, if the mutation is positive, if the PVT1 is positive, you are certain that this is malignant and you know what malignancy it is, go for total thyroidectomy. If the cell-free DNA concentration is high but mutation is negative and the PVT1 is still high, no worries, it is malignancy, go and operate. If the cell-free DNA concentration remains low and the PVT1 is low, mutation is negative, you can just follow up the patient. There's nothing wrong there in terms of malignancy. If the cell-free DNA concentration is low, the PVT1 is low, the mutation is negative, again it's benign. Now if the cell-free DNA is low and the mutation is negative but the PVT1 is still high, these are the ones where you did not have a driver mutation. That's where you should again go and operate. So these are our references, and I would like first of all to thank all of the subjects who participated in our study, my funding agencies without whom of course I would not have been able to do the study. Professor Nitai Bhattacharya is retired director of NIBMG, National Institute of Biomedical Genomics Center. He has been wonderful that he comes to my lab 3 times a week, does not take any money, and is very happy that he's part of our endeavor. And of course the entire research team, Shushmita, who's my PhD student, Shoham, who has been my DM trainee. Incidentally, Shushmita has won the World Cancer Congress Junior Investigator Award for this particular paper. Shoham was last year's European Endocrine Society Young Investigator because he was the DM trainee who actually did it. And the next bit of the study, hopefully I will continue with Astha Mukhopadhyay, who is incidentally daughter of Dr. Pradeep Mukhopadhyay, the current head of IPGMER. Thank you very much.
Take up this study in a long way, in addition to our clinical medicine. I think that's very important. That message is very clear by what you have said. I got one. Now we said that cell-free DNA, that's one of the important tools where we can actually have to follow them up. We do whole body scan and ablation if required and all. Later on, one of the things which you use is thyroglobulin to see if there is residual or recurring thyroid tissue and then do again. So how does this help in the long-term management of the thyroid cancer?
So first of all, I would like to, that's Nizam's Institute in Hyderabad and Amritava Ghosh, who is in AIMS, Raipur. So we are doing 2 things in that study from these 3 centers. We are collecting samples and we are keeping them. Number 1, to detect residual tumor, and number 2, to detect recurrence. Now, I was very excited about recurrence. I no longer am, because I have found several patients where there is cancer, but still this isn't working that well. Now I'll explain why I think that's the case. Because I think we were talking about the mechanisms through which the cell-free DNA is released. So the postulated mechanism that most people think that cell-free DNA is released in circulation in excess is either increased apoptosis or tumor necrosis. Now, you can make out whether it's necrosis or apoptosis by looking at DNA integrity when you are looking. So we've done the DNA integrity study, and I'm not very sure that it is either of the two mechanisms. So there must be some other mechanism. The reason why I'm saying this is, say for example, a follicular thyroid tumor has metastasized to some bone. It is not showing the same biological feature as I wanted it to show. So I'm not very sure, we are doing the study, but I'm not very sure that it's working that way in our ability to detect malignancy. We need more time, but I think at least some of the subtypes we are not able to pick up with the cell-free DNA. Therefore, more studies are needed into the mechanistics of release of cell-free DNA from the thyroid tumor into the blood. The primary tumors, they are working. Now, there are certain theories or hypotheses. I don't know how many of you have read Siddhartha Mukherjee's book, Cancer. So, why does cancer happen? There's a very beautiful paper in Nature that cancer happens because it escapes certain protective mechanisms. One of them is immunological. So there should have been some kind of immune tolerance or immune clearance of the cancer cells, which does not happen in cancer, and that is why cancer happens. So it could well be that when you're looking at a primary thyroid tumor, the immunological defense is unable to clear off the cell-free DNA. But in the case of a recurrence, particularly if it's a distant metastasis, I think there's something that I still don't know. I will accept my negligence and ignore.
I wanted to ask if there is an intact cell, and by the way we do for germline mutations, we lyse the leukocytes and we get the entire complement of the DNA, that versus a cell-free DNA which is automatically released by whatever mechanism the tumor is releasing, is this 100% or we are
Right.
losing some?
I think I started off the mutation. Now, if you're looking at tumor cells coming into circulation and then looking at the DNA in that, that's a different story altogether. But within the thyroid, it is rather unexpected that an intact tumor cell will come into circulation. It's rather unlikely. Had this been some other kind of highly vascular tumor, that might have happened. But in case of a thyroid tumor, I really do not expect an intact thyroid tumor cell will come into circulation, which I will be able to isolate, lyse the cell, and get that DNA. The rest of the white blood cells that we are getting in circulation, that will only give me germline mutations. That will not give me tumor mutations. Because, for example, this mutation that I'm talking about, you take a sample from somewhere else, say a fat cell, you will not get this mutation. This mutation will come specifically from that cancer cell. Yes, Chitra.
Congratulations on
Thank you.
everything and more power to you. Belinda and I said, so this is going to get a Nobel Prize, right?
No, not at all.
That's what we were talking about. My question is very basic, removed from here. So if cell-free DNA is something which is a function of the tumor cell and not a benign cell,
No, I didn't say that. I didn't say that. See, there's a normal process of cell breakdown.
Yeah.
So if you have, I'm just making this up, 100 ml of cell-free DNA in circulation, in you and me, it will come from all kinds of cells. Some cell dead in the liver, some cell dead in the pancreas or whatever, and that's 100 in circulation. Now when someone has a cancer, it will probably become 110.
Okay.
That 100 from rest the places will come. The 10 will come from the cancer cells. So you're looking at those specific cancer cell mutation. So you don't expect to see that mutation in all 100% of the cell-free DNA. It will be only a small proportion of that cell-free DNA which will have that tumor mutation.
Okay. So in the pre and post surgery cell-free DNA study which you did, was there anybody whose cell-free DNA did not normalize? Was that due to some other cause?
Yes. So when we had published the JCM paper, by then all of them had normalized.
Okay.
Then we started picking up 1 or 2 odd patients where the cell-free DNA was not normal. So we went back and re-imaged those individuals. We found that there's some tissue there. We subjected those subjects to another surgery. We took out the tissue from there, reconfirmed in histopathology that the cancer was still there.
Okay.
And we then repeated the cell-free DNA thereafter, after that second surgery, and showed that the cell-free DNA had normalized. So essentially telling us that in the ones where the cell-free DNA did not normalize, there was definite amount of residual cancer cells.
Okay.
So we proved that with histopathology.
Okay.
We proved that after the second surgery that the cell-free DNA was normal.
So is cell-free DNA is not specific to malignancy? It could be tissue breakdown
Yes,
anywhere.
you and I have normal cell-free DNA.
Okay.
You and I have normal cell-free DNA. And, you know, the other two cancers that where people have gone quite a bit, one of them is breast cancer. You will now see there is at least 2 or 3 people. See, basically, I had read that NEJM paper. When I had read that NEJM paper, I had actually gone to Dr. Nitai Bhattacharya, I told you. He was still the director of NIBMG. That was about 5.5 years ago. He said, nothing like this happens. You can't do this. And he literally, you know, told me to leave. But, you know, this PhD student, Shushmita, who joined me, I told her, even before we decide your PhD dissertation, can we try this in a few patients? And we were surprised to see what we found. And we had not thought of concentration at all. Believe me, the concentration bit was an afterthought. We were trying to look at mutations to start with. That was an afterthought.
Okay.
So how many days after surgery?
2 weeks.
2 weeks.
We've done it 2 weeks.
And same routine?
I don't know whether it normalizes in 1 day or 2 days. I don't know why we did 2 weeks, but we just did 2 weeks. That's how, and it worked. It's 2 weeks because we thought, you know, and actually we had a lot of discussion about that, saying that you've done a surgery, there is still inflammatory process going on. I said, okay, let's try the first few. If it normalizes, it normalizes within 2 weeks.
So same you can extrapolate to radioactive iodine operation.
Not that easy, because in the radioactive iodine you are going to damage cells. Once you again have a situation of damaging cells, what happens to cell-free DNA? I don't know. I don't know. I don't know.
So, again, wonderful talk, complicated gene technology made simple. And
it's not complicated. Actually, our basic scientists, they all want us to feel that basic science is complicated. See, I don't need to know. I don't need to know everything.
Simple, though.
I don't need to know everything about basic science. The reason I'm making this statement is because I want everybody in this room to go and do research. You know, all of those databases, I had no idea how to look at those databases. Actually, the students taught me, put in this data here, and it's very simple. You know, they just say, you want to look at long non-coding RNA, put in thyroid. Okay, in that subgroup, go for cancer. Then it will say, these are the 200 long non-coding RNAs. Then you want to say, okay, I want to look at the only studies of those where you have the cell data, where you have the tissue data, where you have the animal data. That 200 becomes 15. Then you say, I want to look at only those where there is a fold change of 2.5 times or more. So that way you narrow down. So because of the fact that we have not had formal training in basic science, we find it overwhelming. It is not, trust me. And I would suggest that the Endocrine Society does a workshop on basic science for clinicians. There's nothing great about it. See, most of them who went there did not crack their entrance exam. Let's be honest about it. So you don't expect that they know much more than us.
Fair enough. So that's great to know. So I mean, this is going to be commercialized if it continues to be.
Roche, I did not know. All of a sudden, I got an email. Roche from Basel, a team of them came to my lab to see whether what we were doing is actually, you know,
possible commercialization.
So what they have suggested to me is they are going to send me blinded samples, and I have to give them reports for validation. But it's a long process. Chitra knows how government of West Bengal works. Believe it or not, the Department of Health did not even have an IPR policy. I'm the one who got a lawyer to frame an intellectual property rights policy to apply for a patent for this.
Long way to go.
Long way to go.
Talk. And the other thing I was thinking is like Dr. Suryanarayan, right? Dr. Suryanarayan is there? I'm just very lucky that I have passed the exam long back. If today I have to appear the exam, it will be like you only. I don't think I can pass this exam with this. Thanks very much. Thank you, Sujay, for coming. And all of us enjoyed very much your talk, obviously. And we'll end the meeting and go for lunch. Thank you. And a special thanks for your Sun Pharma Dapify team for organizing this meeting. I think 2-3 times in a year, if you can keep on doing this, it will be very nice for us. Thank you.
So please book March 9th and 10th.
I'll revert back to you tomorrow.
Yes.